No, still something wrong. And never mind. I'll do something else. Never mind. Okay. Okay, so here you go. So somebody had a question.
Yeah, I had a question. It was about the participation for this week. I didn't have access to like my phone or any sort of camera to take a picture of the moon for about a week. So could I possibly, I just got my phone back. Is there a way I could just take that picture tonight and email it to you?
Let me.
Because it said it was due today by like 4.
Yeah, I know. I'll think about it for a few minutes and let you know before the class ends.
All right, thanks.
Anybody else have any questions or any comments or anything?
I have a question too. I was wondering, where can I find your office hours?
It's Monday and Wednesday from 4 to 6. I am a math tutor. So you have to go to, I'm not sure if Canvas or City College website and look for online tutoring. And specifically look for the mathematics online tutoring.
Okay.
And I'm there from 4 to 6, Monday and Wednesday.
Okay, thank you.
You're welcome. Any other questions? No? Okay. So I want to start this class by asking a question. Does anybody know why the number 7 is known as lucky?
Is it because of the planets?
What about the planets?
There's 7 planets in our system.
Oh, so we have 7 planets?
We have more than 7. I'm just saying, like, it's in our solar system.
No.
I don't know. Is that something? I don't know. I'm just guessing.
You're close. You're close.
Yeah.
Anybody else? Why is 7 considered a lucky number? Number 5. Yeah, Guthrie, you got it. So it does have to do something with planets, but it's that. So many years ago, thousands of years ago, people looked up in the sky and they noticed that basically the stars are fixed. The stars don't move. And even today, they're so far away that for any practical reason, any practical purpose, we consider the stars to be fixed in the sky. They do not move. And we're not going to notice any movement in the stars for a lifetime. Okay, so again, they're fixed in the sky. But people also noticed that there were certain objects in the sky that did move. And specifically, there were 7 objects that were moving in the sky. The sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn. Those 7 objects are moving in the sky. So because of the way humans think, because of the way humans are for thousands of years, they believe that this was some sort of message from the gods that we had 7 moving objects. So they had to honor those 7 objects by making the 7 relevant. And from there we have 7 days of the week. And to this day, a lot of people still believe that number 7 is a lucky number. Even the 7 days of the week are named after those 7 objects. If you know some Latin or if you know Spanish, you would notice that we start with Monday. Monday, day of the moon. Tuesday in Spanish is martes, Mars. Wednesday in Spanish is miércoles, Mercury. Thursday is jueves, Jupiter. Friday is viernes, Venus. Saturday, Saturn, and Sunday. Those 7 days of the week are named after the 7 objects that are moving in the sky. Okay, now a related question. Okay, so you might be able to guess the answer, but why is 12 so relevant? Number 12. We got 12 apostles, 12 months of the year, a dozen, and I don't know what else. 12. Why is 12 relevant? Anybody?
Zodiac sign?
Well, we have 12 zodiac signs, but number 12 was relevant before the zodiac signs.
Is it like an even number that divides in or something like that, or not?
There's something to it, but no, it was
No
more of a
divide.
coincidence.
Okay.
What you mentioned right now is the reason why they use 60, the number 60 for minutes.
Yeah, that's why I was like, so it's
Because
divided by 12. Yeah.
you divide it a lot of ways. Well, the reason we have 12, in case you haven't noticed, is because there's 12 average, there's 12 cycles of the moon in a year. There's 12 full moons in 1 year on the average. Sometimes there's 13, but on the average, we have 12 full moons in a year. So people looking up in the sky, they noticed that after 12 full moons, the seasons came back. A certain season came back after 12 full moons. And that's why they divided the entire year into 12 months. They call it months. The word months has to do with the moon, by the way. And throughout history, different civilizations, different cultures have divided the year into 12 periods because of the moon. Today, we're going to be talking about those months, and we're going to be talking about days. So let's start with the month. So we define two different months. And I'm going to share my screen with you so I can write down a few things. Okay, so we have something called a, no, before that, hold on, before that. In the documents that I put on Canvas, I tried to explain this. If you have something, anything, in this case, if you got a planet that is spinning around, an obvious question would be, how do you know exactly when it's completed one full turn? Okay, well, first of all, if I put a line on it, if I put any type of mark, I would know that this thing has completed a full circle when, after going around like this, it comes back to the same position. When this line, this mark right here comes back to the same position, I know that it's completed a full circle. Of course, in order to do that, I also have to put a mark outside of that circle. When those two lines line up, if you will, when those two lines line up, I know it's completed a full circle. Okay? So this same idea is used to define a complete circle, a complete revolution, or a complete rotation, or a complete orbit in astronomy. The same idea. So you're looking up in the sky and you see the moon. There's the moon. After, you'll notice that the moon, every night, every single night, it moves a little bit towards the east, a little bit towards the east. And I'll explain that later why. After a few days, you don't see the moon anymore. And then after another few days, you're going to see the moon every day rising again until it comes back to a certain position. So how do we know that the moon has completed a full cycle in the sky? Well, there's two ways. One is we look at the face of the moon. We look at the face of the moon and we say that the moon has completed a full cycle, full lunar cycle, when it goes from one full moon to another full moon. Of course, you can use any other phase of the moon. You can either use full moon or new moon. Those are the ones that are most commonly used. So it goes from one full moon to another full moon, or from one new moon to another new moon. That's what we define as a lunar month. But this one has a very specific name. This month, when you use the face of the moon to measure the time, this is called a synodic month. A synodic month is the time from one full moon to another full moon, or from one new moon to another new moon. That is called a synodic month. And the time it takes the moon 29.5 days. Not exactly, we're just rounding it. A synodic month is 29.5 days. In other words, the amount of time between one full moon and another full moon is 29.5 days. As you can see, it's almost a month. But instead of looking at the face of the moon, what we can do is, and now I'm going to stop sharing this. If I can. Oh, there it is. I'm going to stop sharing this. And I'm going to share Stellarium. There's Stellarium, and there you go. So let's get rid of a few things. Let's get rid of the atmosphere. And let's go find the moon. So wherever the moon may be. So there's the sun. And moon should be right. Come on, moon. There's the moon. Let's put it over here. Right there. Okay. There's the moon. And let's do this. Let's put up a, let's do, I'm trying to find, oh, here it is. Okay. Let's see if we can get the moon closer to another star. I'm trying to place the moon right next to some star. Some known star. Okay, I think. No, I don't like this. Okay, let's use this. Let's see if this works. There we go. Okay, so look at this star. This star is called Regulus. Look where the moon is. Okay, and kind of look at that distance between the two. So now we're going to count the number of the time it takes for the moon to come back to this exact position. Okay, and we're going to go day by day. So let's move one day forward. Oh, we're moving in. No, I should be moving this one. There we go. Let's go back a little bit. Forgot to mention. There we go. Okay, we'll put it right there. Okay, so look at the date. The date is October 13, and look at the time, 9:20. Okay, look at the distance between the moon and Regulus, right there. Okay, now we're gonna start moving in days. October 13, 14, 15, 16, 17, 18, 19, 20. That's 7 days. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 days. 21, 22, 23, 24, 25, 26, 27. 27. A little more than 27 days. A little more than 27 days. So it takes, if we use a star as reference, instead of using the phases of the moon, if we use a star as reference, then the moon goes a full cycle around us in less time. So I'm going to stop sharing this, and I'm going to share the other one. So if we use a star as reference, it takes the moon 27.3 days to complete a full cycle. And this is known as a sidereal month. So there's two types of months by definition. One is a sidereal month, and that is 27.3 days. And another one is the synodic month, which takes 29.5 days. Two different months. Sidereal month is based on the position of the moon with respect to a star, any star in the sky. And synodic month is the position, the time it takes for the month to go from one phase, like the full moon, to another full moon. Okay. Now, I'm going to stop sharing this. There you go. And let's go back to, I'm going to go back to stellarium, because just like we define 2 different months, we also define 2 different days. We all work with something we know as a typical day for us lasts 24 hours, but that is not entirely true. Let me show you. First, I'm going to get rid of the atmosphere because it just gets in the way. And next, we're going to put up these lines. This line, see this line right here? That line would be known as the celestial meridian. It's a line that goes from south to north. It goes all the way around and passes by the zenith. There's the zenith. So this would be the celestial meridian. Now I'm going to go and move until I find the sun. There's the sun. Okay. There's the sun. And I'm going to move in time so I can place the sun right on the celestial meridian. There it is. The celestial meridian is cutting the sun in half. Right there. Look at the time. 12:45. 12:45, maybe 12:46. 12:46, okay? There it is. 12:46. The sun is right on the celestial meridian. Now we're going to move in time, okay? We're going to count the number of hours it takes for the sun to come back exactly here. So we're going to move in time. Here we go. Nine, 10, 11, and 12. Look at that. Exactly 24 hours later, the sun is exactly on the celestial meridian again. That's how we define a day, the usual day that we work with. And the usual day we work with, because we use the celestial meridian as a reference, that one is known as a synodic day. Just like the synodic month, this one is known as the synodic day. A synodic day is the time it takes for the sun to cross the celestial meridian twice. And it's exactly 24 hours. I take it back. It's not exactly 24 hours. 24 hours and a very tiny fraction of a second. And because there's a slight difference, astronomer or the people who take care of the time, they go through, they check the position of the sun every day. And sometimes they have to add a second or even take away a second to our clocks so that we always use a 24-hour day. But again, that's one way of measuring the day, but there's another way of measuring a day. And the other way of measuring a day is just like in a sidereal month, is by using the stars as reference. Okay, so watch this. I'm going to, let's see. Oh, here it is. Look at this one. You know this star, Antares. Okay, now I'm going to move Antares and I'm going to place it right on the celestial meridian. No, I'm sorry, not the celestial meridian. Yeah, I'm going to place it on the celestial meridian. There it is, almost. Right there. There's Antares on the celestial meridian. Okay. Antares on the celestial meridian. So now I'm going to move again. I'm going to move in time, 24 hours, and see what happens. Look at the star. Look where it is, okay? Antares. I'm going to move up 24 hours. '23 and 24. Look at that. Antares is a little bit beyond the celestial meridian. In order to be on the celestial meridian, I have to go back 1, 2, 3, 4 minutes, almost 4 minutes, a little less than 4 minutes. So this is known as the sidereal day. The sidereal day is the time it takes for a star to cycle through and go back to exactly the same position. That's a sidereal day. And this sidereal day is 23 hours and 56 minutes. 23 hours and 56 minutes. Now I'm going to try and explain what's going on. So I'm going to stop sharing, close this, and share my screen again. I'm just going to write a few things here. A synodic day is when the sun, it's 24 hours long, and it's the time it takes the sun to cross the celestial meridian twice or 2 consecutive times. A sidereal day is the time it takes, it's 23 hours and 56 minutes long, and it's the time it takes for a star to go back to the exact position. "23 hours and 56 minutes long." Now I'm going to try and explain why. Okay. Here's the sun. There's the sun right there. And here's the orbit of Earth. There's Earth's orbit, okay? And let's put the Earth right here. I'm exaggerating the sizes, but here's Earth, okay? And Earth is pointing to the sun, and at the same time is pointing out to a star. There's a star. Oh, this is really bad. Let me get this a little better. There we go. There's a star, okay? And I'm gonna cross this as well, like this. There it is. So after 24 hours, oh, wait a second, no. After 23 hours and 56 minutes, we're going to see this star again after 23 hours and 56 minutes. We're going to see that star again, okay? But, and remember, keep in mind that this star is very, very, very far away, extremely far away. So this drawing is not very good, but it's extremely far away. So 23 hours later, Earth is going to be right about here. And it will be pointing straight to that star again. Ah. Okay, no problem. Get rid of this and get rid of this. So after 23 hours, the Earth is going to be looking at that star again. But look, over on this side, it's not pointing to the sun because Earth is going around in its orbit. So it's going to be looking at the star, but it's not going to be looking at the sun. And you're going to need an extra 4 minutes, of rotation for the Earth to be looking at the sun. That's why a synodic day is 24 hours, but a sidereal day that has to do with star is 23 and 56 minutes. I hope that makes sense. If it doesn't make sense, let me know now. Okay. No questions. Let's go back to I can hear some music. I don't know who's playing music. Okay, I'm stop sharing that. Okay, any questions up to that point? No questions? Okay, now I want you to do a little, so up to this point, the only thing I've done is define what a synodic and sidereal month and day is. That's something you need to know. Synodic month, sidereal month, synodic day, sidereal day. That's the only thing so far that we have defined today. Now I need you to do a little exercise. It's gonna be simple, very simple, okay? I'm not gonna give you any clues yet. I'll give you a clue in a couple of minutes if you get stuck, but for now, let's try it this way. And whatever your answer is, I want you to give me a reason of why. The question is, as you look up in the sky, you see the objects moving across the sky, okay? And the way we measure the distance they cover in the sky, we say they cover a certain amount of degrees because they're going around in a circle, okay? So we say that the moon is half a degree wide. And we say that the sun has moved 20 degrees, 30 degrees, 40 degrees, whatever, okay? So the question is, how many degrees does the Earth spin around, rotate in 1 hour? How many degrees does the Earth rotate in 1 hour? Approximately, of course. Anybody make a guess?
23 degrees.
23 degrees. Close, but no.
I'm gonna say 50.
Why? I'm sorry, who said 23 degrees?
Yesenia.
Yesenia. Why Yesenia? Do you have a reason, or just because it's one of the numbers we've been using?
The altitude of the sun at noon. I think it has to do with that concept.
Well, not bad, but no. Anybody else?
I have an idea. I think it's 15 because in 24 hours, the Earth rotates at 360 degrees, like a forward motion. So
That's exactly correct. And Guthrie also had it. That's exactly correct. Let me put up my share so you can, I'll try and explain it. It's very simple. Very, very easy. So the Earth goes, here's the Earth. And if you're standing right here, you're going to go around like this, a full circle in 24 hours. And a full circle is also 360 degrees. So if you go around 360 degrees in 24 hours, all you have to do is divide 360 by 24, and it'll give you 15 degrees. So this is a number you have to memorize. This question is going to appear in 1 or 2 or maybe even 3 quizzes in the future. How many degrees does the Earth spin around or rotate every hour? And the answer is 15. I hope you're taking note of this. Okay, now another question. How many degrees approximately does a star move in the sky every hour? How many degrees does a star move in the sky every hour? Anybody?
I think it's the same, no? 15 degrees.
Maria, is that you, Maria?
Yeah.
A little louder, Maria, please. We can't hear you.
I think it's the same, like that.
Maria, that's very
that's
good. That's excellent. It is. It's exactly the same number.
Yeah.
And for exactly the same reason.
Yeah.
Because if the stars are fixed in the sky and we are going around and the stars are fixed, the stars seem to move because we are moving. We are the ones who are moving, not the stars. So the stars are going to be, they're going to seem like they're moving at 15 degrees every hour also. Okay, very good, very good. So notice how there's 2 possible questions with the same answer for the same reason. How many degrees does Earth spin around every hour? 15. How many degrees do the stars seem to move in the sky every hour? 15. Now, the planets, the moon and the sun, they move at a slightly different speed. But at least for one night, they move approximately 15 degrees every hour. The moon is the one that moves a little bit crazy. I'll give you the number. It's a little difficult to understand why, but the moon actually moves 13 degrees every hour. 13. Okay, here's another question. And this one is, well, I will not give you any hints this time. Okay. How many degrees approximately does Earth move in its orbit around the sun every day? How many degrees does the Earth move around the sun every day? Anybody? Yes, Jake. Anybody else? Well, let me show you. Here's the sun again. There's the sun. And here's Earth. By the way, Earth goes around the sun almost a circle. It's not really a circle. It's an ellipse, but it's close to a circle. And because it's close to a circle, it's 360 degrees. And the Earth goes around the sun in 365 days. So if it goes around 360 degrees in 365 days, it is approximately 1 degree every day. A little less than 1. But for us, it's going to be 1. We're going to approximate it to 1. Okay, so here's a few questions. Okay. I'm not going to explain them until we get the answers. So you look up in the sky, let's say early in the evening, and you look towards the east where the sun just, towards the east, the sun already is setting in the west. You look towards the east and you see a certain constellation, any constellation, doesn't matter. Matter of fact, you don't see the entire constellation. You see one of the stars of a famous constellation, okay? Let's say it is, let's say the star, I'm gonna have to share my screen again. Okay, you look at, and the star rises, and by rise I mean you see it exactly on the horizon at, let's say exactly at 7 p.m. Okay, you see the star rise exactly at 7 p.m. Question: at what time? At what time is that star, that same star, what time is that star going to rise tomorrow? The star rises at 7 p.m. tonight. So tomorrow, what time is it going to rise?
$7:01?
No.
Oh.
Tomorrow is going to rise at 6:56. Remember
The 4 minute, yeah.
the 4 minutes, yes. The 4 minutes. So because when we position the stars, when you use the stars as reference, they go back to the same position in 23 hours and 56 minutes. So the star is going to be at that same position, just rising 23 hours and 56 minutes later, which is 4 minutes earlier, if you will. 4 minutes earlier. Okay. At what time is the star going to rise a month from today? At what time is that same star going to rise a month from today? Well, if it rises 4 minutes earlier every day in a month, 30 days on the average, is going to rise 120 minutes earlier, which is 2 hours. So 1 month from today, it's going to rise at 5 p.m. I guarantee this will be a question in some quiz. 2 questions, actually. One of the questions is, if it rises today at whatever hour, 7 p.m., what time is it going to rise tomorrow? 4 minutes earlier. And what time is it going to rise in a month? 2 hours earlier. Or what time is it going to rise in 2 weeks? That would be 1 hour earlier.
Professor,
Yes.
if it only takes 23 hours and 56 minutes for it to travel 360 degrees, wouldn't it travel more than 15 degrees in an hour?
Oh, wait. With respect to the stars, the answer would be yes. With respect to the sun, the answer would be no. So it depends on what are you using as your reference point. Are you using the sun? It takes 15 degrees. If you're using the stars, it takes a little more than 15 degrees. But for all practical purposes, we can think of it as 15 degrees because the difference is fractions of a second.
Okay, cool.
Does that answer your question?
Yeah, thank you.
Okay. Now, going back to this rising of a star, I could ask the same question with a constellation. I could say, for example, if Sagittarius rises today at 7 p.m., what time is it going to rise a month from today? And the answer is 5 p.m., 2 hours earlier, because remember that a constellation is made up of stars. Let me think. There's another question. 7 minutes, the 4 minutes. Okay. Okay. Questions with this? Do you have any questions? What we're doing today is talking about measuring time in astronomy, at least with some objects. In summary, we define what a month is. There's 2 types of months, synodic and sidereal. We define what a day is, also synodic and sidereal. We define how many degrees the Earth moves in its orbit every day, approximately 1. And we define how many the rising and setting of stars every day. And one last thing I would like to say is, no, I'm not going to go. I was going to try and explain why the moon travels so differently, but that's something we're not interested in. So don't worry about it. Okay. Any questions? Any questions that you might have? Because that covers our class for today. I'm sorry, I can barely hear you.
Sorry, it's not a question, but I was just going to say that Mars is really close to Earth. I mean, it was last night and I guess early today. But I saw in the app that I use, I think Starwalk 2, it had said that Mars was really close to Earth. And it won't be this close again until 2035.
Let me try and explain that real quick.
Okay.
It's not that difficult. So let me give it a shot real quick. So here's the orbit of Earth. Of course, the sun is in the middle. And here's the orbit of Mars. Okay. And they do not go around in their orbit at the same time. So sometimes Earth could be here and Mars over here. And Earth goes around like this. Mars keeps going around like this. Sometimes Earth could be over here. Earth could be over here, and Mars could be way over here. But sometimes every I don't know how many years, it turns out that Earth and Mars are right here. And when that happens, that's when we see Mars really big, very big. And that's what happened. Actually, Mars right now is not that close. It was this close, I think it was early this year. It was really close like this. Right now, it's a little bit farther away. It's more like this right now. But it was very close a few months ago. Now, every year, around this time, you'll see it on the internet. Every year, somebody puts out a message saying that the Mars is going to be close, and it's going to be so big that it's going to be as big as a full moon. And that is totally false, completely false. Mars can never get that big. So don't believe it. Okay, you're welcome. Any other questions? Anything at all? Either about this or about anything else?
Yeah, I had a question.
Go ahead.
About the participation thing. I tried to take a picture of the moon last night.
Oh, yes.
And I couldn't do that because it was
You're
at
the
eye
one who
level
told me, right?
and there was all these trees.
Okay, what I'll do is I will reopen that participation because I've got news that some people have been having trouble because of the fog as well. So I will reopen that participation starting today. As soon as we end the class, I'll open it for another 36 hours. So you're going to have 2 nights, 2 extra nights to do it. 48 hours, 2 days. Is that okay?
Yeah, thank you.
You're welcome. Anything else?
What camera are we supposed to be doing? Because in the instructions you said something about a specific...
Well, I've been encouraging you to use your cell phone, and I would prefer that you use your cell phone. But if you have an DSLR or even a mirrorless camera, go ahead, use it. It's going to be a better photograph.
One more question, Professor.
Go ahead.
You had said that the week 6 participation was a selfie with the moon, which was due on September 29th. But then you'd also said you added to the week 6 module that this like detailed photograph of the moon was due today at 4 p.m.
There were two participations, 2 different ones.
Okay.
One was a selfie. Just take a selfie with the moon in the background. But this time, the new participation was taking a good photograph of the moon. And by good, I mean, I don't want it to be just a white blob.
Right.
I want to be able to see some detail on it.
Right. And with the fog, if we weren't able to get a good picture or get a picture, would you extend the assignment or no?
I just did 5 minutes ago. I said it.
Okay, cool.
I'm going to extend it 2 nights.
Okay, thank you.
Hopefully the fog will clear up a little bit. Oh, but wait a second. Wait. Don't go away. Hold on a second. Problem is that the moon is rising very late now. So you're going to see the moon, and it's not going to be a full moon. And you're going to see it around maybe midnight.
Ooh.
Oh, yeah.
That's pretty late.
That is very late. So, you know what? Let's do this. I will allow I will reopen this participation in about 2 weeks so that you have the opportunity to take a photograph at an earlier time. Does that make sense?
Yes, it does. Thank you very much.
Okay. But please, anybody, remind me in 2 weeks, just in case. But I'll make a note of it, and I'll reopen it in 2 weeks so that you can have a better photograph.
Thanks.
Okay?
Thank you.
You're welcome. Anything else? Anything about astronomy? If not, then we are done. And I wish you all a good night, a great weekend.
Thank you.
Take care, and we'll talk soon.
Have a good weekend, Professor.
You too. Thank you very much.
Bye.
Bye-bye.
Thank you.
You're welcome.
Profesor,
Dígame.
sí me equivoqué, vi mal mi horario porque tengo 4 clases.
Ajá.
Y pensé que lo del test era para las 5 de la tarde y era otra clase.
¿De qué estamos hablando, María?
Del test del estelario del viernes.
Sí.
Que vi mal mis schedules porque tengo 4 clases y su clase se cerró a la 1 de la mañana.
Sí.
Y yo me equivoqué al ver mis otros assignments, pero no sé si podemos hacer algo más.
Había alguien más que me dijo exactamente lo mismo. Iván.
Yeah.
Were you in the same problem?
Yeah, but it actually turned out there was an assignment that was set at 5 and I just got them confused.
Okay, so you did not complete the quiz either?
No.
Okay. I will set up a makeup quiz. Not the same quiz. I'll set up a makeup quiz later in the semester for those people who missed a quiz. Does that help?
Wait, yes, thank you.
¿Sí, María? ¿Sí?
Sí.
¿Le sirve?
Ajá.
Okay.
Sí, muchas gracias.
No hay de qué. Is that okay, Evan?
Bye.
Yeah.
Okay, I'll take care of it then.
Thank you.
Okay, have a good night.